Okay folks, last video in this module, we are going to build up the d orbitals with the basis set and function in R, just like we did for the p orbitals. Let's do it. This should be fun. Okay, for the d orbitals, and just like we started with the pz previously, we're now going to start with the dz. And as it turns out, this one ends up being the dz squared, corresponding to the ml equals 0 state. So we could write psi dz squared as psi 320, or r32 times y20, and that equals some function in R, which will be different than what we got for p, different than the p orbitals, right? It has to be. But within the set of d orbitals, that function in R must be the same. And so what you'll notice is the dz squared is not just z squared times f of R. It's a little bit more complicated than that. And so recall now that that z squared will be r squared cosine squared of theta. So we're going to look for that. So now plugging all of this in, we can say psi dz squared, and I guess 3dz squared more specifically, is going to be the r32, which is this 1 over root 2430 times z over the Bohr radius 3/2 times rho squared, which now we recognize rho for 3 for n is equal to 3 will be 2 over 3 zr over a naught. So now that's rho squared. So I'm just going to note that that's 2 over 3 times z over a naught. And I'm going to square that, and I'm going to write out separately an r squared. And then now that's e to the negative rho divided by 2. So that's just going to become negative zr over 3 a naught. So the 2 canceled with the 2 up there. And then finally, that's times the yl ml. So now that's times all of those constants, 5 over 16 pi, 1/2, times 3 cosine squared theta minus 1. So I'm not going to go through this trying to simplify this algebraically, but what I do want to point out here is you'll notice that when we distribute this cosine squared minus 1, we're going to end up with a 3 r squared cosine squared theta, right? Which is exactly what we got right there. And then, of course, that will be minus 1, so minus that r squared. So that's where the 3z squared minus r squared comes from, right? R squared cosine squared of theta will just become z squared. Beautiful. So what does that one look like? So here it is. And in this case, because we have no imaginary numbers, we can just take the square of the wave function. And we see this lovely shape here. And once again, we have different phases of our wave function based on where this spherical coordinate solution maps out on the XYZ Cartesian. So our different phases go as the following: positive, negative, positive. Okay. Which I know seems counterintuitive, but we'll see the manifestation of that as we go further down the rabbit hole. So now looking ahead to the other d orbitals, we can make a set of the, so I think I have that on this one, the 3dx squared minus y squared and the 3dxy. So as it turns out, the psi dxy does just in fact end up equaling xy times f of r, and that's the same function in R that we would get for 3dz squared. The dx squared minus y squared ends up being 1/2 times the quantity x squared minus y squared times the same function in R. And so now we build up our basis set with the following. We will define the ml plus 2 and ml minus 2 states as such, the d plus 2 and the d minus 2. We create a basis set by looking at the positive, negative contributions. And so we can say then that the wave function for d squared minus y squared equals 1 over root 2, right? That is our normalization constant of the d plus 2 state plus the d minus 2 state. And if we were to work through the algebra, we would arrive at that 1/2 times the quantity x squared minus y squared and the same function in r. And now we can get the dxy orbital with another normalization constant, 1 over I root 2. And now this time it's d plus 2 minus d minus 2. And if we work through all of that algebra, we would find that that works out to be xy times the same function in r. And so remember that x and y are combinations of sines and cosines. And so now if we were to look at these, here you can see I've got my 3dx squared minus y squared. We get this lovely shape, right? The 4 lobes that looks like our d orbital. And similarly, we could look at the dxy, and we get a similar situation. And now with our phases, the way that we can interpret this here, so notice I've got the 0 line on my graph, right, indicating the Cartesian dependence. So we can see like this lobe out here is in the positive corridor, so that will have a positive phase. Across the way down here, that orbital will be in the negative corridor, so it will have a positive phase. Next door to it, this orbital is in the negative coordinate, so it will have a negative phase. And similarly, this orbital will be in the negative positive coordinate, giving it a negative phase. So we'll see the same alternating pattern of positive negative phases in these solutions. So we can do the same thing for the ML plus 1 and ML minus 1 states, which make up the dyz and the dzx, which I have up here. So now similarly, the ML plus 1 and the ML minus 1 wave functions go as the following. We create a basis set with the plus minus possibilities. And now when we look at those basis set and go through the algebra of all of this, our dyz, in fact, becomes yz times a function in r, and our dzx becomes some function zx times f of r, and we get the exact same shapes, albeit with different phase dependencies. So those pictures end up looking something like this with all of their respective equations and alternating phases. And if I put them all together in this Mathematica file, which you can see right there, it looks pretty cool, right? You can see that they all find a little nook and cranny to fill themselves in. And so I want to stress again that this is the one electron system, right? We're not necessarily putting an orbital on every single last one of these little lobes. If we were to do that, this would change the shape of these things. But overall, this is a good approximation to what perhaps a full D shell atom might look like. So more or less, it looks like a sphere, right? It's got like symmetry all around the X, Y, Z axes. Okay, cool stuff, folks. That is the end of this module. We will be moving into multi-electron systems next.